the first ever detection of a gravitationally lensed gravitational wave event might have just happened. Every first ever is pretty cool in science, whatever it is, but this is especially cool because if we could routinely measure lensing of gravitational waves, we could use that to measure all sorts of other important things, like the Hubble constant and precision tests of gravity, to name just two. One of the interesting things you will hear about in today's talk is an improved modeling of the candidate lens. This better nails down the probability that the wave really was lensed, and even more fun, gives insight into what astrophysical things the source and lens could be. Today we're joined by Miguel Zumalacarregui from the Max Planck Institute for Gravitational Physics in Potsdam, Germany. Welcome everyone, and welcome Miguel. Do you want to start by briefly telling us about your paper?
Right, Sean. So in this paper, we analyze a remarkable gravitational wave event under the hypothesis that it was gravitationally lensed. And what we find is that it's not definitely, but a very compelling candidate for the first lensed gravitational wave from stellar mass black holes.
That sounds incredibly exciting. Other than maybe the obvious that this would be the first time, I guess, that this has been seen or heard, or however one's supposed to describe a gravitational wave. Are there any other reasons why this is perhaps important? Like, are there things we can now do that we can't, or is it more of a kind of proof of concept? And once we've got 100 of these, we can do cool stuff.
Well, there are things we can do now. So one of the outcomes of our work is that we can place this event farther away because of gravitational magnification. So it could be a peak beyond the detector horizon and a peak into the population that we will observe with upcoming upgrades. And also we are probing the object that's doing the lensing, which is very intriguing. It has to be at least 200 solar masses, maybe more in the 1,000 solar masses. So this could be an intermediate mass black hole or even a dark matter object. These are things that we can start to unveil with a single event. And of course, as these detections become more common, there will be many other applications.
Okay, let's have a very quick intro into the results here. How is it that you are confident that you've seen a black hole lensed on its way here?
Well, confidence comes from the statistical analysis, and it's, of course, is not definite proof. I will go into what could provide this more definite proof. But this is compelling because we have seen this black hole under the no lensing hypothesis. It's shown here. This is the posteriors as a function of the total source mass and the redshift for this particular event, which is the most massive, and it also has very high spin and discrepancies between different models of the waveform. This is true even when we account for measurement errors, but once we include gravitational lens, in this case, I'm showing the posteriors of a single isolated point mass. You can see it in the bottom, where I'm showing the Einstein ring on the lens plane. This shifts the posteriors towards masses and redshifts that are much more consistent with previously found events. And it also is favored by a bias factor that is at least order 10 and order 1,000 in some other, even higher in other models. And it removes all the discrepancies between the signal models. Now, what's really unique about our analysis is we can, for the first time, consider a non-symmetric lens. So you can look how the Einstein ring now, by the action of an external potential, bends into an elongated shape. And this is a more realistic situation, as I will show later, representing the external potential of the galaxy in which this object is embedded. And this accounts for magnification, allowing us, under some assumptions, to put the event even at higher redshift and lower intrinsic masses, and also remaining favored and as an extension of the previous model, keeping all the nice features in terms of bringing back agreement between waveform approximants. What's very interesting too is that the object that produces the Einstein ring, it has to be at least 500 solar masses in the isolated case, and at least 200 solar masses in the case we have an external potential. So it's a very mysterious object we need to invoke there.
I'm not going to badger you about this now, so people can wait until discussion when you're actually presenting the results. But I guess just because the base factor is bigger, my immediate skepticism is that if the situation itself of having this very, very massive lens is equally unlikely, then it kind of maybe weighs it out. But stay around to later on to see Miguel's answer to that. In the meantime, was there anything particularly confusing that's still lingering in your understanding of these results?
Well, the most confusing thing is the nature of the lens, this 200 to 1,000 solar mass object. This is, as you hinted at, we believe that this should be very rare if they are of astrophysical origin, but it could also be something more exotic, like a dark matter. Many dark matter theories predict the formation of dense objects with different masses. So this is a potential interpretation. There's also a limitation in the theory that we have. We cannot do this analysis for a realistic distribution of stars. So it could be that hundreds or thousands of stars that or remnants with more realistic masses, maybe in the 1 to 10 solar masses, could mimic the effect of a larger object.
Let's get deeper into the background now. So why did you do this in a bit more detail, and what questions were unanswered that you wanted to solve, and why are these important and relevant in 2025?
Well, as you know, gravitational lensing is a very important tool to understand, to interpret astronomical observations, and also to learn about astrophysics, fundamental physics. So, and gravitational waves offer new opportunities. So lensing is well known. Here you can see it in real life as the two images of a single olive in a martini, and also in astronomy as in the bottom image as multiple images of a galaxy behind a galaxy cluster that are highly distorted. Now, when we include gravitational waves, they are coherent signals with very long wavelengths. And this allows us to look into new effects such as diffraction and interference. And this particular event looks like this. So here I'm showing the strain. This is how far the detector is stretched as a gravitational wave passes through as a function of time. And this signal, 231123, recorded a couple of years ago, was reported as having the strongest support for distorted lens signal by the LIGO-Virgo-Cagra collaboration. So I've been thinking about this for, half a decade at least. So I was very excited. And same as we can see in these images on the left how we can resolve in space how the olive or the galaxy are split. But with gravitational waves, we have very poor angular resolution. So our way to look into these multiple images or distortions is through time resolution and theoretical models. In particular, our analysis shows that our best fit corresponds to decomposing this signal into a main image, shown here on the top, and then a secondary image with a smaller amplitude, but basically the same shape, and a third component, which is entirely a diffraction feature, which is distorted and would not be there if the source had much higher frequency or the lens was much bigger. This is something that's very unique to gravitational astronomy.
And the reason is it completely obvious why one doesn't talk about diffraction features with optical lensing, which I mean optical wavelengths are, what are they, like nanometers or whatever? So we're talking about cosmological scales. It's just completely ridiculously different scales, whereas the gravitational waves have wavelengths that are not nanometers.
That's right. The gravitational waves have wavelengths that are thousands of kilometers. And what matters is the comparison between the wavelength and the gravitational radius of the lens, or the Schwarzschild radius. So for optical lenses, this is a point of concern, but you need objects that are below asteroid masses, so 10 to the minus 10 and under for optical observations. You hear of these for people who are searching for primordial black holes, for instance, on microlensing light curves and similar observations.
suppose they must have stuff like this with lensed radio waves, I suppose.
That's right. In the case of radio waves, you can push that up to planetary scale lenses. So I mean, 10 to the minus 3 and under solar masses. But this has not been observed. And one of the reasons is that radio waves, these planetary masses, are subdominant with respect to stars for lensing of radio waves. And also radio waves interact with ionized matter. So there's additional dispersion effects that for CHIME and radio observatories and pulsar observatories are much more important at this moment.
Is the secondary image, I mean, like waveform sound, that's exactly the same as with this kind of strong lensing picture you had where you like see two visual images of the galaxy, like one of these sound waveforms has come around one side of the lens and the other one's come around the other side. It's the same kind of.
That's right. And what you have, the diffraction feature, is the thing that goes around the lens in not a clearly defined path. There are several reasons why we can do this lensing analysis with gravitational waves. The first one is that the signal is coherent. We observe the amplitude and phase of the gravitational field in time. This would be different in an extended source. There would be superposition of emission from different parts of the object that would blur these effects. And so you can imagine how this is important to have such a crisp amplitude evolution. The two other properties is that the signal is predictable from first principles. So we have tools such as post-Newtonian theory, numerical relativity that allows us to simulate black hole systems or neutron stars and extract a very definite prediction. You can see in this video how this system, this was the very first black hole recorded by LIGO Virgo detectors. And you can see how it evolves from an in spiral, and then the black holes collide and then ring down into a larger black hole. The other property is that this signature can not only be computed, but it has a rich structure that traces the underlying properties of the objects emitting it. We can measure the masses, we can measure the spins, we can measure orbital properties such as eccentricity and precession. This is ultimately because black holes are so simple. They're characterized by each black hole by just a couple parameters. And together, these properties allows us to distinguish lensing and do the type of decomposition that I showed before.
On the screen, you've obviously shown, I guess, what the theory predicts, but in reality, I guess this is buried under a lot of noise. So are the like error bars on each of these parameters still quite large, or is it actually really precise?
It depends a lot on the event. So for lower mass systems, you have a longer signal in band, they evolve more slowly, and then you can typically constrain at least some of these parameters quite accurately. For instance, there's a combination of the masses called the chirp mass that determines the phase evolution that can be measured very well, especially for lighter systems. The other factor is the signal to noise ratio. So the louder, the better. Something remarkable about this event is very short. So we don't have, it's quite loud. So signal to noise ratio of about 20, but it's quite short. It's less than about 0.1 seconds in band, just a few cycles. But even then, there are constraints on many of these parameters. And they're broad, but they're not orders of magnitude broad. Let me take you on the journey of a lens gravitational wave, which, as you can see in this diagram, it's will be deflected by an intervening object. Gravitational waves, like any messengers, will be affected by gravitational fields along their trajectory, as shown in this diagram: deflected, magnified, distorted, and delayed. So gravitational waves are very unique in that they encode the final moments of a binary system in the waveform. As the signals travel through the universe, they can encounter massive objects such as a galaxy. And the gravitational field of these objects will produce focusing on the radiation, which will lead to amplification or magnification of the signal, which very importantly is achromatic. It does not distort the shape of the signal because it does not depend on the frequency. Now we can zoom in into this galaxy and there will be a great deal of small-scale objects such as stars, planets, compact objects, and also dark matter halos. These objects will produce distortions of the wavefront that are in the wave optics regime, such as diffraction and interference, which lead to chromatic effects. Chromatic, they depend on the wavelength and therefore on the frequency. So as the signal evolves in frequency, this will lead to a distortion. And we can use these signatures, these frequency-dependent modifications, to identify and study lens gravitational waves, as we have done with this candidate.
When you say that the primary lensing is independent of frequency, is that a Newtonian approximation, or would that also be true at like a GR level where there might be like time delay things going on? I guess it would still be independent of frequency, but would change the frequency. Is that?
This is general relativistic. It's a weak field in the sense that we're considering a linear potential, but it's general relativistic. There will be a time delay overall with respect to an unlensed image, or if there are different trajectories of multiple images, there will be different time delays and a relative time difference. And there will be a gravitational redshift, kind of like an integrated Sachs-Wolf effect, but this is very small. And in the case that the lens is static, so if the gravitational potential is in equilibrium, the blue shift and the red shift will cancel out. So we're not looking into these effects. The reason for this to be frequency independent is because this is in the ray optics regime. So each can talk about this later, but each ray, like each signal, can be described as a very specific path, like as a ray. Whereas if we look at diffraction, we are in a regime where the wavelength is comparable to the time delays, or the gravitational radius of the wavelength is comparable to the gravitational radii of the objects.
Just going back to the kind of like classic optical strong lens situation where you see like 2 or 3 images behind the lens. In principle, there's like a fourth one that would have just gone straight to you, but because it's optical and has such a small small wavelength, it just gets blocked. But this is precisely that image that is then this interesting diffraction one, the one that actually pointed straight at the lens. But because it has a much larger wavelength, it doesn't get blocked. It kind of diffracts around it, like a water wave going past like a thing in the water.
Right, that's the diffraction features. This would be caused by the smaller objects, and this will happen on all the images as long as they encounter such objects, and it can be very subtle. I think you're referring to the central images, which is very interesting. So if the lens, the macroscopic lens, like the galaxy, is not singular, there will be a path that goes very close to the center, but it's usually very demagnified. So it's two things. It's demagnified, and in the case of electromagnetic observations, it's behind like opaque and bright regions. So it's usually, for a galaxy certainly, is very hard to discern. But it's something that is one of the interesting applications of gravitational waves.
Cool. Well, you've certainly convinced us that these things are out there in the universe happening. Some gravitational waves are being lensed, but how here on Earth can we, predict these signals and extract these signals so that we can say with confidence we have actually measured a lensed gravitational wave?
In a little bit more detail, these wave optical phenomena depend on 2 dimensionless quantities. The first thing we need to consider is the Einstein angle, which is very well known. This is how we measure the offset of the images or of the source relative to the lens. But we have a different axis here, which is the dimensionless frequency, which is you want, is measured by the wavelength, so the size of the gravitational radius of the lens divided by the wavelength. And I'm showing a third quantity here, which is the amplification factor. That is, to make this well defined, we consider the ratio of the unlensed signal, so the lens signal to the unlensed signal in the frequency domain. So this diagram here is showing how the amplification factor, or its modulus, depends on both the impact parameter in units of the Einstein radius and the dimensionless frequency. And what you can see is that the smaller the impact parameter, the stronger the amplification. There's some interesting interference that we can discuss later at higher frequencies. But also, if we go to very low frequencies, lensing is very suppressed. Like if we go to very small dimensionless frequency, even if the lens and the source are very closely aligned, low impact parameter, we get basically no lensing. And this is the idea, heuristically, that a wave is not perturbed by objects that are smaller than its wavelength. Just goes through. There's two ways to observe this. One is if the lens is moving, we can, at constant frequency, we can go through this pattern. But we're more interested on the case in which there's frequency evolution or chirping.
The reason why one can even make a figure like this is that you've assumed a point lens and you've kind of factored out the mass of the lens. So, it's not a different plot for every mass of the lens, that the X and Y axes are like functions of the mass of the lens. So you have the one plot that, if you know the mass of the lens, you can now give units to the X and Y axis instead of them being...
That is right. Yeah, everything is rescaled by the mass of the lens. Normally, we know the frequency, but we don't know the mass. So this is precisely, we observe a certain frequency and frequency evolution around 100 Hertz. And from that, we can infer the mass of the object. Right, so we're interested in frequency evolution, and this is the example. This is for a LISA massive black hole binary, but illustrates the typical regime. So it's for a particular choice of source and lens, where we go from at very low frequencies, no magnification, the waves just go through, and at higher frequencies, there's a diffraction pattern, and this looks like a modulation, but in reality, this is just the superposition of two images on top of each other. And this will be more clear when I show a time domain example. One thing is, this is very complex to compute, and this has been a limiting factor in this type of analysis. So I want to advertise that my collaborators and I have developed a code, GLOW, or gravitational lensing of waves, that makes these calculations much faster and flexible and easy. And you can find it on GitHub. So in a little bit more detail, and the reason why this calculation is complicated is that the amplification factor is an integral of a phase, so an exponential of the dimensionless frequency that's proportional to the mass. That's how the mass gets rescaled, times the Fermat potential, which encodes the time delay for trajectories around the lens. Now, in the case in which the frequency is very high, we can this very complex non-convergent integral can be solved by the stationary phase approximation, where only critical, so stationary points of the Fermat potential or the time delay contribute. Just basically Fermat's principle. You can think of just the maxima, minima, and saddle points of the time delay contributing, and every other point leads to it's cancelled by destructive interference of many waves. And this is the first term that you show in the second equality. It's just a sum over, could be one, could be more images with a certain amplitude, which is the square root of the magnification, mu, and a certain time delay, and perhaps also a phase. But in general, there's an additional contribution, shown here as the last term, wave optics, that encodes diffraction. And if the wavelength and the wavelength of the source signal and the gravitational radius of the lens are commensurate, this is not negligible, as is the case of this example. Yeah, the figure below shows on the left the amplification factor in the frequency domain, and on the right there's the time domain correspondence. This is just a Fourier transform of one another. And this shows how different, in this case, the frequency is fixed for a typical black hole merger, but I'm showing different masses. So the panel labeled A is for a 3 solar mass object, where there's this corresponds to the low dimensionless frequency band, and this causes a subtle modulation of the signal. So there's slightly higher amplitude at higher frequency. The intermediate panel, labeled B, has a 300 solar mass lens. This is closer to what we're observing, and then you can see that there's an interesting modulation that goes up and down. You can see this in the frequency domain and also on the time domain. And then in the right panel, it's 30,000 solar masses, so it's a much heavier object. In this case, you can see that the signal gets split into two images that have a different amplitude and a characteristic time delay. So this corresponds to what looks like these very rapid oscillations in the frequency domain. It's just the superposition of two delta functions in the time domain, or two exponentials in the frequency domain.
I guess you're going to get to this, but the key thing to me, already leaping out to me, is you've of course shown, especially in I guess this middle orangey yellow one, how different it is when the lensing is there. But the question isn't how different is the unlensed and lensed. It's how different is the lensed from a different mass unlensed one. How can you tease out those two?
Exactly. As you said, the key here is to distinguish the color curve from all the space of black curves that correspond to different masses, spins, and other properties that we might consider. And this is what parameter estimation will do. So crucially, these lensing signatures depend on the Fermat potential, or the time delay, and this depends on the lens model. So the step ahead that our work does over the state of the art is to consider a single isolated lens, a point-like mass, embedded in an external potential. This is a very well-known case in gravitational lensing, goes back to the late 70s by Chang and Repsval. And it includes, the first line here shows the external potential where there is a convergence field or isotropic distortion of the lens. This is the effect of a constant homogeneous mass density. And then there's an additional component, the shear, which you can see distorts with the way we've chosen the coordinates, distorts the x direction, the x1 direction in the opposite way as the x2 direction. So that's the first line, the external potential. The second line contains a point mass. That's the lensing potential, the gravitational potential integrated along the line of sight of a point-like object. You can see there's no mass. The mass has been reabsorbed into the dimensionless frequency, but this is characterized by two quantities. One is the offset between the image or the source, the projected position of the source, and this lens. And the other one is the angle that the optical axis forms relative to the external potential. Below, you can see a render of this configuration where the two parameters are shown. And you can see that this shows the lens plane and how the Einstein ring, in the presence of external magnification, gets distorted by this external shear. So this is a potential that it's sort of realistic in the sense that it's what we expect if a smaller object is embedded in a galaxy or a cluster, and it leads to much richer phenomenology. But it's also asymmetric, and this, because computing wave optics lensing is very challenging, this has been very difficult to do as an application to data analysis. And this is where our code, our algorithms come to play.
So when you say external potential, I mean, that phrase could mean just about anything, like for the shape, the asymmetry, the profile, blah, blah, blah. Am I right to say that the top line is kind of an expansion in parameters, and that to capture any external potential with very complicated features, you might need to go convergence, shear, next order, next order, next order, next order. But this is assuming that the external potential is somehow relatively smooth and only a small deviation, and so then you can capture it with the two parameters, the convergence and the shear.
That is absolutely right. That is the leading order contribution from an external potential that varies on scales much larger than, say, the Einstein radius of the smaller object. You could expand this, you could add, it's known as flexion. When you add cubic terms, you could add more complex potentials for highly magnified images. So this is kind of like the vanilla situation where we have like a larger, like a smoothly varying gravitational potential.
The second line, I presume, is just exact, because like it's a point mass, you can calculate it precisely.
Exactly. Yeah. The other thing that we're neglecting is in a realistic situation, there would be the analog of the second line. There would be a third, a fourth, probably hundreds of additional point lenses, additional stars, compact objects that would also contribute. In this case, this is something that we don't know how to do yet, and we're neglecting. Yeah, and well, there's a technical point is we're assuming a specific type of macroscopic potential where the convergence and the shear is positive in this case, is smaller than one. And this means that the macroscopic, so the smaller object, the lens is located in a global minimum of the macroscopic lensing potential. This is usually, it's known as a type 1 image. This is usually the brighter one. This always form, so it's quite generic. You don't need to form multiple images. And it's usually brighter than, say, an unlensed signal. Yeah, the lens mass does not appear in this potential, but in the rescale frequency, as shown here. And we're also only sensitive to the redshifted lens mass. So there's a 1 plus redshift of the lens factor with respect to the intrinsic lens mass. Another important point is that out of these 5 free parameters, one of them is completely degenerate with the distance. The convergence, so the homogeneous distortion of the field, or constant homogeneous density of matter, cannot be measured by wave optics distortions or anything we can do with lensing, really. This is well known in lensing. It's known as the mass sheet degeneracy. In our case, the effect is to rescale the amplitude, so it's degenerate with the distance. And we can deal with an amplification factor, F, where we remove this parameter that we cannot measure and rescale the external shear and the impact parameter of the lens by a factor that's shown there. This is a fundamental limitation. In lensing studies, people who do lensing time delays struggle a lot with deals and have come with methods to overcome it, usually looking at kinematics of the lens galaxy or other like probes other than lensing. In our case, we cannot do that because we cannot, the sky localization is very bad. We don't know where the lens is. So I will quote model-independent results where no assumption is made, and I will also assume a typical lens, which is a singular isothermal sphere, where the density is singular at the center. And this is, on one hand, a fair approximation, like it's simplified, but it's reasonable approximation as a first step to a galactic scale lens. And it also gives a well-defined relationship between the convergence and the shear that allows us to break this degeneracy. Equipped with this model, we can do Bayesian analysis. And I will look at 9 separate cases. This means we analyze 3 different models for the gravitational wave signal as emitted by the binary system. One is numerical relativity surrogate. This is for this type of merger is, and it was shown by LIGO Virgo Kagra to be the one that best reproduces the simulation results. So it's the one I will focus mostly on, but because there were discrepancies between different signal models, I will also look at two other ones, the surrogate effective one body and phenomenological precessing, also known as XPHM. On the other axis, I will look at three cases with respect to the lens model. So first, we will look at the unlensed signal, as shown in the LIGO Virgo Kagra original paper. Then we will look at the isolated point mass. This adds two parameters, the mass and the offset between the lens and the source. And this is the kind of standard analysis that has been done by other groups, including the LIGO Virgo Kagra collaboration. And what's unique about our analysis is the point mass plus external potential that I explained in the previous slide with 4 additional parameters. These are nested models. So each model is a direct extension of the former one. So the data could always go back to the simpler model. We're not forcing anything. Everything is direct extension. We will also use the usual priors for the source parameters, but we will use flat priors on the lens parameters. This is could be done differently, could be reweighted, but we believe this is the most agnostic thing we can do in terms of astrophysics. And to highlight our results in terms of the significance, I will start by saying that we find high bias factors, always with respect to the unlensed hypothesis in a case-by-case basis. For the numerical relativity surrogate model, they are in the ballpark of 6 to 800. The surrogate effective one body has lower bias factors. This is driven by the fact that they fit the unlensed model better. Then the bias factor is 13 to 17. And then in the phenomenological precessing HPHM case, the bias factors are huge. This is again driven by the fact that the unlensed model is a much worse fit. And I've arranged this table from best to worst agreement with numerical relativity simulation. This is why from now on, for the most part, I'll focus on the NR surrogate, which has the smallest deviation with respect to signals that people can predict numerically.
Some pieces of this I think I might need unpacked. These very, very different Bayes factors from left to right. Is that essentially telling me that these three models I cannot be compatible with each other? Like they're not all relatively accurately described. Like I was expecting the three columns to be almost the same because they're just minor deviations, but they must be very different physics.
That's absolutely right. This was one of the remarkable properties of this event is that different signal models gave quite different results. They have different parameters, and the reason for this is that the unlensed interpretation, the unlensed analysis of this model requires quite high spins. So very rapidly rotating black holes. And this pushes the analysis into a region that is very poorly calibrated, so there are very few numerical relativities, or it's much harder to do numerical relativity simulations with high spins. The models have not been as well developed and tested. So it's and it's one of the things that happens when you include lensing is that it's not necessarily evidence for lensing, but I find it interesting, at least, that these discrepancies between models get mitigated. So you go to a region with more moderate spins, and then this becomes a lot less of an issue. These differences are driven by the unlensed model.
Do we a priori expect that high spins are unlikely?
Depends who you ask. They are unlikely with respect to previously observed events. Now, the LIGO Virgo Kagra analysis, they determine that this is not an outlier in the sense of being, they have some threshold of significance with respect to the population. So, but it's close to an outlier, both in spin and masses. There are ways to have a highly spinning black hole. For example, if black holes, the components of this binary have formed as they are second or third generation black holes, they will have high spins. My understanding is that the spins are too high for them to be second generation black holes. So they could be third or subsequent generation, which there's been a number of papers exploring that. High spin can also be a product of accretion. It could be that black holes, the components have had accretion disks in their history that has spun them up. One caveat to this analysis is that the data is noisy. So there's noise fluctuations, non-Gaussianities in the data that make us be often a little skeptical of bias factors because these noise fluctuations can translate into important changes in the bias factors. So this is something that's often done in gravitational wave literature, is to simulate the event in the unlensed case, so unlensed signals, and we recover with the lens model, and we ask ourselves for different realizations of the noise, and we ask ourselves what is the distribution of bias factors for this type of events. And this is shown in the bottom. It's the inverse conditional distribution function for this bias factor, so this probability distribution for 100 realizations. It's costly, so we cannot do much more than that. And you can see that typically the bias factors are shown in the histograms are smaller than the values we found again for the numerical relativity surrogates. So we can say at this point that the false alarm probability is smaller than 1%. And in this sense, I would say the analysis for the lengthening hypothesis is compelling.
Can I try and understand one piece of that? This is kind of by its nature an extreme event, right? Like it wasn't that it was picked at random from the sample of black hole mergers that we have detected. When you say the false alarm probability is less than 1%, is that saying that if we observe gravitational wave events for 6 years, the probability that the most interesting one is a false alarm is less than 1%? I'd have thought that the probability that the most interesting one, where the noise just are on the 450-second gravitational wave detection faked this, might actually be higher than 1%. Is that a sensible question? Do you know the answer?
So this 1% refers to events that are, if this was an unlensed event of this type, like this mass range, like a short event with the typical levels of noise. So less than 1 in 100 similar events with similar masses, etc., will have a bias factor as high as what we have found. But this refers to the posteriors of our event.
But is my question making sense that if we make 100 observations, we would find one of them that's interesting, and then we do this analysis on it, and say it's 1 in 100? Is that not? Is there not some selection bias going on here?
So there's two layers here. One is the event itself has a false alarm probability. This was quoted by the team that did the search, I believe. So the entire event being entirely due to coincident noise is, I believe, below that than a chance of 1 in 10,000 years. So the event is, there's a black hole there, I have no doubt. The question is for these finer features of the, is it lens, is it not, is it lens by a point lens or a point lens with an external potential. That's what we're addressing here. So if you were to have 100 events with these type of properties, which are unlikely in the population, so they're already, at the far end of the mass distribution. So it's there would be a factor there. Then out of 100, probably more, because you see that in the tail of this diagram, we didn't manage to sample all the way to the bias factor that the data is giving us. So conservatively, 1 in 100 could have by chance this type of mimic this type of signature at this significance. But it's hard to relate this to the entire population because this is a relatively rare event, like in terms of mass, at least.
Yeah, I guess I'm thinking about these things like Eddington bias, where less interesting things due to noise can look like more interesting things. So the question would be, you don't want to look at the population of 100 interesting things. You also want to look at the much, much larger population of uninteresting things and say, can they accidentally mimic the interesting thing? And I don't mean mimic like there being a signal at all. I mean mimic a boring signal looking like an interesting signal.
I guess what you're asking is if this could be transformed into a global number. So not just for this one particular set of posteriors, uh, but with respect to the entire population.
These questions are notoriously impossible, though, because there's so much human factor involved, right? Like, as soon as you have a posteriorily decided to look at this, how do you model that? You can't model an entire community finding something interesting. So it's actually an impossible question. But I'm not pushing back on this being interesting. Just that 1% maybe accidentally isn't taking this other stuff into account that's completely unquantifiable.
Absolutely. And this is, I believe this, is clearly the highest evidence in lensing we've had so far. There's another issue, which is in gravitational wave astronomy. I mean, this is a bit of a tangent, but you search events by comparing signal models with data and looking for coincident triggers and like weighing them a certain way, and then this gives you do that with the data shifted, so you can compute random chance, like events that shouldn't be there just by chance, by noise. So this is very well established, but this is done with simple waveforms that do not incorporate this type of effects. So in this, when it comes to lensing, diffraction, distortions, I think the fact that we have found an event is not something I expected. I think this event that's distorted will be more likely to be classified as a noise artifact. Yeah, going back to the analysis, I mentioned at the beginning that there were some uh, inconsistencies in the unlensed analysis between different signal models. So, and you can see this here on the left. I'm showing the chirp mass. This is the combination of masses that determines the frequency evolution. And you can see that there's discrepancy between the numerical relativity surrogate and the phenomenological model. The same is true for even something as basic as the luminosity distance, that is how far the source is. You would think this is the amplitude, this is given by the amplitude of the signal. But even in this case, this can be pretty different between these two analyses. And these discrepancies, once you include lensing, this is true for the point lens or the embedded point lens, these discrepancies sort of go away. There's a combination of the posteriors are wider, of course, because the model has been expanded. And then the posteriors get shifted towards regions where the signal models agree more with one another.
You said earlier when I asked like why is this happening that it's because they're not good at modeling high spin and this is being pushed into a high spin area. What are the chances that like how similar are the like physics? No, not physics. Physics is the right word. How similar are the effects on the signal? Because could your lensing model be accidentally modeling spin? Because if the answer to that is no, then this is very convincing. If the answer to that is yeah, maybe, then yeah, then I guess it's less convincing.
There is some degeneracy between lensing and spin, in the sense that lensing causes modulation of the signal, and spin precession in particular causes the orbital plane to bounce up and down, and this also changes the amplitude of the signal. Typically, we expect this to be discernible. There's some degeneracy, but it's not a full degeneracy by any means, because precession changes the phase evolution in ways that lensing don't. In this case, there's some degeneracy, but the analysis prefers lensing over such high spins. The analysis still has some spin. The spin is non-negligible for most of the posterior, but it's not higher than 0.8. It's not in the region where these signal models disagree with one another. Another surprising feature is that the sky localization is much wider for the lensing analysis. So the unlensed region gives this gray area, which is quite big, even for the standards of gravitational wave astronomy. But once we include the lens, we do not only change the masses, the intrinsic masses and distances to the source, but also we vastly increase the region in the sky where this event could have originated. And there's also a shift on the highest likelihood region.
Not knowing well enough how the localization is done, I thought it had something to do with multiple detection places on Earth and then kind of triangulating. Naively, I wouldn't have thought that that would have affected that.
I'm happy to explain. So it's true that localization comes from a combination of triangulation, so arrival times to different detectors, and antenna pattern. The detectors have different better or worse response depending on the sky position. So normally you would not think that this affects. So one problem with this event is that Virgo was not operational during the first observing run. There were some issues that thankfully have been fixed. So sky localization is worse than it could have been. But there's another aspect, because the unlensed signal is so spinning. I believe this also constrains haven't studied this in a lot of detail, but this also constrains the spinning and precession properties are related with the inclination angle at merger. And the inclination angle could play a role. Like if this is overly constrained because of the high spin in the unlensed case, this could give a artificially small posterior, whereas in the lens case there's more room for the for many of the parameters. For the spin, there's more room for the inclination, the angles that refer to the orientation of the source.
Seeing as you're talking about localization now, I guess I think I had a question that I think I also answered. I was going to ask, can we not kind of, if we know what the object's mass and things are, can we not look for similar types of objects? But it's not like a galaxy or a galaxy cluster mass, is it? It's like a lot of stars mass, and so that's not something that's necessarily just going to be able to be found with an optical telescope and said, oh, it's that guy over there, I guess.
That's right. Where we are constraining is the small lens, so 200 to 2000 solar masses. So that's small, very small feature of a larger lens, say a galaxy. There are ideas to try to use catalogs of known strong lenses to localize lens gravitational waves. The problem is there are many such lenses. So I don't think this is going to work very well for this event unless we find additional images. Like I will get back to that later. So I think there would be certainly thousands, if not more. Another aspect we can learn about is the microlens. So that's the object that's producing the diffraction. In our case, well, we can constrain all the parameters, the source parameters, and the 4 additional parameters. In the left, you can see the redshifted lens mass. This is under two waveform models for the most complete lens analysis with external potential, and they broadly agree. On the right, you can see the external potential. Here I'm showing assuming that this singular isothermal sphere, macroscopic lens, so that the 2 parameters are equal to each other. Didn't mention we can constrain the angle between the shear and the optical axis. I was very surprised by that. And we can also, given our posteriors, we can infer the true distance to the source. And then under some reasonable assumptions, we can infer the intrinsic mass of the lens. Remember that there's a redshift factor in the quantity that we measure best with respect to the intrinsic mass. So assuming that the lens is between us and the source, and its redshift probability is weighted by the Einstein radius, we can constrain it and get values that are smaller by a factor 1 plus lens redshift. This is shown on the left for the case with an external potential and the isolated case. And you can see that the fact that the source is a higher redshift gives, and also the lens redshift is a little lower, gives us a lighter lens, which is more plausible from an astrophysical point of view. If it's a single object, we expect many more objects with lighter masses. Another aspect that's interesting is that the physical offset between the microlens, this few hundred solar mass object, and the image can be much larger by a factor of about 4 with respect to the isolated case. And this is important because this increases the probability. The probability goes like the offset squared. It's like an area quantity. So it's number of density of lenses times the separation, the radial separation squared. So it's an order of magnitude more likely to have this type of phenomenon in the case with an external potential versus the isolated case. In this case, in this sense, it's a more plausible situation. Plus, we expect the external potential is expected whenever we have an object embedded into a larger host like a galaxy. So yeah, this raises a very important question, which is what in the universe is the micro lens? What we can say is that everything is compatible with a point lens. We haven't looked at extended lenses. This is also future prospect. But if it's astrophysical, then it has more than 200 solar masses. So it could be an intermediate mass black hole. We could compute the probability of these using some predictions. I don't believe there are many observations for black holes in this mass range other than gravitational waves. It could also be an extended object, like a stellar cluster that's dense at the center, or a globular cluster. In this case, we have to keep in mind that the mass that we measure with lensing is not the total mass of the system, but the mass within the Einstein radius. So it's not impossible that an object that's much bigger, be tens of thousands, hundreds of thousands of solar masses, if it's dense, has an effective mass that's in the few hundreds to a couple thousand. This is also a possibility. We cannot rule that out. Perhaps more intriguing, this could be a dark matter object. We did an extension of our analysis where we compute the abundances of these, the abundance of dark matter objects, compact dark matter that you would need to explain these observations. And here we take into account that there are many events where no lensing signatures have been observed or at much significance. And I'm showing here two results. One is the dashed line is if we can exclude for those events that a lens of a certain mass is present up to 1 Einstein radius, or in the field contours if the lens can be excluded up to 2 Einstein radius. This, which is more, maybe it's a little bit more aggressive, but it's also in line with what we found in this event where we have look at the impact parameter, we measure it at about 2 Einstein radius and can be constrained to higher values. So I've also compiled some of the constraints that are available in the literature around this mass range. So it does not, is not a very it's not a very clear interpretation given other constraints. It's in tension with microlensing of stars. It's in tension with dynamics. It's within 2-3 sigma of those constraints. There might be ways around it. So the stellar microlensing looks at objects in the Milky Way halo. So if this is a dark matter theory that does form compact objects, but maybe only in, say, in galaxy clusters. This could be like some self-interacting dark matter have these properties. The dynamics constraints refer to ultra-faint dwarf galaxies, so much lighter systems. So there could be ways around it.
Sorry, just to translate the gist of this, the idea is that if the thing that caused the lens existed in sufficient abundance that we've actually observed a lensed gravitational wave, that it should be there in sufficient abundance that these other probes would have seen similar objects.
With, some error bars and some posteriors that extend further. There's another aspect. So I'm not showing constraints from the cosmic microwave background, which are typically stronger for compact objects. Well, for very compact objects like primordial black holes. So I'm not showing them because these could be quite compact, but not actual black holes, in which case the CMB constraints are less stringent. And this could also be dark matter objects that form after recombination. So another thing we can address to some extent is whether there are additional macroscopic images. So this would correspond to the situation in which the source and the lens are closely aligned, and therefore there are different trajectories around the macroscopic lens that, with a certain time delay, that we would observe as separate gravitational wave events. So there would be gravitational wave 231123 would be one event, and then there could be more with same intrinsic properties coming before and after, but different overall amplitude, and also perhaps different lensing distortions due to smaller scale objects. So again, assuming that the lens is a singular isothermal sphere, which is simple model for a galaxy lens and could be extended, we can convert the external potential to an offset, so an impact parameter between the host, so the source itself, and the lens galaxy. And within this very simple model, arc posterior is 75 of arc posterior is compatible with an additional signal forming in the first place, and 55% is compatible with this additional signal having a signal to noise ratio higher than 8 that we could, in principle, or should detect as another event.
And with a time delay of an unknown amount, or are we talking weeks, years, decades, minutes?
So it's a spherical lens model, so it's not. But if it's a galaxy of 10 to the 12 solar mass, so galaxy plus halo, similar to the Milky Way, it would be a few days, the time delay. But of course, it's proportional to the mass. If this were lensed by a galaxy cluster, even a more realistic galaxy cluster, the time delays would be years, maybe even decades. If it's a lighter galaxy, it could be smaller.
Yeah, and just to maybe you said this and I missed it, but the idea is that the 200 solar mass object is inside a galaxy cluster, and so because the alignment was good for the 200 solar mass object to do some strong lensing, probably so is the bigger object, and therefore you would get the multiple images by the little guy, but then you'd also get multiple images by the big guy.
Exactly. So you have the multiple images by the little guy delayed by order 20 milliseconds. That was this diffraction and multiple images. And then the multiple images by the big guy delayed by days if it's a galaxy, or years if it's a cluster.
So yeah, where are we going to next? How should what are you planning on doing next, and how should we in the community be kind of updating our actions based on your research?
The main issue with our analysis and this type of analysis is that we don't have the tools to do this in full realism. So the most important thing that we need to do is look for additional lensing signatures that can help confirm or disprove that this was like a gravitational lens black hole binary merger. So one aspect is to improve the lens model. So I was looking at a like a spherical micro lens of 200 solar masses, but in reality, we expect that the macroscopic lens will have a very complex stellar field with hundreds or thousands of objects. So we need to be able to analyze that to either find additional signatures. So in addition to the multiple images, could be that there's multiple images by a larger object. This could still be true, but then there will be additional contributions in the form of diffraction by the smaller lenses. The other thing that we want to learn is whether more realistic stellar distribution could mimic a larger object, and how likely that is. This is questions that we need to begin answering, and I'm very much looking forward to do. The second axis is to search for additional images of this event. I alluded to some predictions in the case in which the lens is of a certain type, like a spherical, galactic, symmetric potential, but this doesn't need to be the case. We need to search for additional images, keeping in mind that they could be sub-threshold, so they could be very faint to be normally classified as a proper gravitational wave event, and they could also be distorted. So in our case, we found substantial distortion. It could be, or a combination of both. It could be a sub-threshold distorted signal. And then the fact that it's distorted is going to push the ranking statistics down to lower its significance.
Will it be distorted in the same way as the original, or probably not, because it's not going to go through that same smaller object. It'll go through some other path. So we don't really know the predicted distortion. But I guess we do know some degree of prediction of the unlensed initial signal. Like, we don't know the precise one, but we know some. So I guess what I'm getting at is it's sub-threshold when you don't know the actual original signal, but maybe you can find the needle in the haystack if you know what the needle looks like.
Exactly. That's exactly right. So we should be looking for an object whose intrinsic properties are compatible. They're going to have different posteriors, but the posteriors should be compatible. The sky localization should be compatible. And then we can refine the search. The sub-threshold search works because instead of looking through, say, a year of data, we're weighting that year of data to, if it's a galactic lens, to, say, a week of the around the main event, or even if it's a year of data, we know the properties. So we can lower the signal to noise. This is something that many groups have developed. In this case, also the distortions will not be common, but it would be a smoking gun. If we find another signal that is distorted in a lensing way, as in diffraction, interference, I think this would be, a lower probability of this happening by chance to two events that have the same morphology. That's why, for me, this would be the real smoking gun. As an additional outlook, once we can complete the picture, we can look for sources beyond the detector horizon. So here's going back to the main diagram. I'm showing the posterior of this event with the external magnification. I'm showing the entire population down to a couple solar masses, and the detector horizon that we expect for the next observing run, if they finally can upgrade the detectors. And there are forecasts that say that we should have 1 to 10 lens gravitational waves per year at that sensitivity if the rate follows the star formation history. And the mass and redshift distribution will be as shown in the green contour. But of course, we could also observe sources at much higher redshift. For example, remnants from population 3 stars that form much earlier in the universe history, and even primordial black holes, if they exist. As another twist, there's a growing interest into lensing multi-messenger detections. So lens neutron stars are a very exciting target too. They're expected to have observable kilonovae. They would, if we catch them, we can do, for example, cosmography. So time delay cosmography, where the time delays has millisecond accuracy. That's many orders of magnitude, four or five orders of magnitude better than the state of the art. But and there's a program to do this. There's believe Rubin Observatory has a target of opportunity for this type of observations, but they will be, even at upcoming sensitivity, well beyond the detector horizon with magnification factors of typically 100. And then magnification, as I've shown here, our magnification is like between 1 like close to 1 and 10 on the upper end of our posteriors. This is easily an order of magnitude higher. So distortions will be very important to analyze these signals whenever they happen. Thus, to conclude, we have analyzed this very unusual gravitational wave event with, for the first time, lensing potential that is not symmetric. It includes the effect of gravitational magnification by a larger object that we can constrain. And it allows us to trade an unusual source with a very high mass and spin with an unusual lens, which is at least a couple hundred solar masses and could be an astrophysical object, could be dark matter. But something I'd like to highlight is that every modeling detail that we've added to our analysis makes the lensing hypothesis more compelling. Not necessarily in a pure statistic, false alarm probability sort of way, but in the fact that you can constrain more properties about the system. You can learn more, and wouldn't be surprised if by improving this model again, by allowing for smaller objects around the main lens, we could learn more things about this particular system.
What work being done in cosmology is particularly interesting, but underappreciated by the community.
Right. So now I'm focusing mainly on gravitational lensing and gravitational waves, but I used to be 100% on dark energy and test of GR just a few years ago. So I'm very excited by the DESI and supernova results on evolving dark energy. And I think that something that's relatively underappreciated is the trying to explain these results within a consistent theory of gravity, by which I mean a Lagrangian, like writing a Lagrangian that tries to explain both the background history as suggested by this dynamical dark energy evidence, and also incorporate the structure formation. So Lagrangian based modeling for dark energy dynamics, I think it's something that more people should be doing. There's very interesting works that I'm very excited whenever I see something. And the advantage also of doing dynamical modeling, dynamical theories with a Lagrangian is that you can incorporate other tests like laboratory and also gravitational wave-based signatures.
So yeah, thanks everyone for watching. If you like this, subscribe, do all that cool stuff. If you have any questions or suggestions, leave a comment. Otherwise, check out whatever recent talk I've decided to advertise right now. And thanks, Miguel, for the great talk.
Thanks a lot, Sean. It's been my pleasure.